Right, so if we are going to look at how a telescope works, we need to encounter something called a lens, and the plural of a lens is lenses. Got a few pictures here to show you different uses of lenses. Got a magnifying glass here, a pair of glasses, here's a contact lens, and this is a telescope. So we've got a couple of lenses here that are combined together. What we're going to do is have a little look at what individual lenses are. Each of these are single lenses. So this is one single lens that we look through. Here there's actually two lenses here, but they're used as single lenses. Your left eye goes through one lens, your right eye goes through another lens. Same with your contact lenses. But what a telescope does is it combines two lenses together. So the light from a distant object passes through two lenses, and we use that to do what we discussed in the previous video. By shining that light through two lenses, we get the magnification, we get the clarity, we get all the information, and we absorb or collect more light than we would have done otherwise. So let's have a look at lenses in order to then understand telescopes. So before we do that, a couple of questions. Have a go at answering them. Why are lenses used in cameras? What's the point of a lens? And why are lenses used in telescopes?
Just stop the tape.
To answer these questions, this example I showed in the previous video, this shows the problem with why a pinhole camera can't then be used for a telescope, or practically why we don't bother using pinhole cameras in everyday life. And the problem here is that when we use a larger gap, or when we want, and the reason for using a larger gap is to let more light in, but if you use a large gap here, you end up with blurred regions on the film here and here, and you don't get a nice crisp clear image, you get a blurry image. So we want to collect lots of light, but we want to focus it to make sure that it's not blurry, and that's what we can do with a lens. This is just a sort of cartoon here that shows light coming from an object, and when it passes through a lens has a property that it can focus that light from this single point here to a set single point here. And if we place the film exactly at that point where the light is being focused to, if we place the film here, then we get a very crisp, very clear image, and we can record what we're seeing out here. If the film is put in the wrong place, here or here, then we don't get a crisp, clear image, we get a blurry image, which was still the problem we were having before. So the lens is good because it can focus light. Okay, so two types of lenses that we're going to have a look at: convex lenses and concave lenses. So these are so called because of their shape. A convex lens is wider in the middle than it is at the two ends, at the top or at the bottom, and a concave lens is wider at the top than it is in the middle. Concave curves inward, convex caves outward. And the way I always remember the difference is that this is a bit like a cave, which is a curve sort of into the mountainside. Okay. Also, we might see them like this. So biconvex, bi, which means two, like on a bicycle, or binoculars, or whatever. So it's got two convex sides. This one's plano, it's a plane, it's straight, and it's convex. Biconcave, two concave, or plano, straight edge, and concave. Both can have the same effect, and what they do is that they can manipulate light. So how do they manipulate light? This is how a convex lens manipulates light. It causes the light to move in towards one single point. So this is convex. But another way that you might hear this referred to is a convergent lens, because the light converges onto a single point. This is different from our concave lens here, which I've got a picture of. So concave, but this is sometimes referred to as, you might also hear it, a divergent lens. because as the light comes in here, it then spreads out as it goes through and passes on the other side. It diverges. All right. Now both of these images that I've just gone through, they've got a couple of things here mentioned, the focal point and focal length. We're going to have a look at those in a minute. But firstly, what we want to try and do is I want us to try and understand, why does a convex lens have this effect? Why does a divergent or a concave lens have this effect? So I'd like you please to have a little think. Do you know why a lens has this effect on light, and why is the lens able to change the direction of light in this way?
Stop the tape.
Okay, so the reason this happens, the reason that this effect occurs, is because light is a wave. And waves have certain properties and behave in certain ways. Light is an electromagnetic wave. But electromagnetic waves behave similarly to other types of waves, such as water waves. Now, the easiest way for us to think about this is to try to imagine water waves and transfer that model for light waves, because it does work. This is a picture of some water waves in a tank, and as you can see, we've got sort of the crests or the tops of the waves here, which I'm just highlighting in red, or they're white ones here, and then the troughs or the lowest points in the waves that will be in between here, which I'm putting in green. So we've got here our waves that they're traveling along, and a wavelength, you'll remember, is that's the distance between adjacent crests here. That's given the symbol lambda. That's the wavelength. Okay, so here we've got waves, and in this image we've got waves, and it's a photograph taken of a bunch of waves that are traveling from the left to the right. Okay, now what I'm going to introduce here is a glass block into the situation. So if you had this exact same situation here and I stick a glass block in the way, let's observe the effects. So the waves that are passing nowhere near the block, they continue normally. They travel through like this. But the waves that strike the block experience a change in direction as they go through. What was a wave coming in straight like this has now changed direction. Also, we've got here a large wavelength which is consistent, and it's the same all the time. With this change in direction, we get a change in wavelength as well. So as light passes from, as these waves, which are water waves, as they pass from travelling through water to then travelling in this over this glass block, there's a change in the direction and in the wavelength. So here we've this photograph between these two situations shows water waves travelling along normally, and then water waves travelling over this glass block here. We get two effects. We get a change in direction, and we get a change in wavelength. This is an effect that happens for all different types of waves, and it is called refraction. Change in direction and change in wavelength. So this happens in water, but it also happens with light travelling in different mediums. So we know that light travels through air. That's the reason we see stuff, because light is bouncing from those objects into our eyes, and our eyes notice that thing. Light also travels through glass, and we know that because I can see things from outside of the window. When I look out of the window, I can see my beautiful garden, and the things in the garden are reflecting light that travels through the air, then through the glass, and then through the air again and into my eyes. But there is a slight direction as light travels, a slight change in direction and in wavelength as light moves from one medium to another. That change, again, it's called refraction. Light changes direction and it changes wavelength when it moves from one medium to another. it's an effect that takes place with all waves when it goes from one medium to another. Now, why does this happen with light? Why does light refract from air to glass? Well, it's to do with how dense are air and glass. So air is a gas. We've got lots of particles all spread out. Inside our glass, we've got a more firm structure, a rigid structure, and the light it collides with more electrons in this process. I'll do some blue electrons here actually. It collides with more free electrons as it moves through here. And so because it's interacting with the electrons in here, it actually ends up slowing it down. And that is what results in the change of speed, and the change of speed means we get a change of direction. I'm going to show you this slide as well. This is a model that is sometimes used to help people to imagine what's happening. And this, we're imagining here that our truck, this is the light truck, and here we've got, this is equivalent of the air and the glass. Okay, now if you imagine a truck moving from the concrete surface here onto this muddy surface, or light from air into glass, what's going to happen when this truck first hits the mud? Well, this wheel here hits the mud first, so this side is going to slow down, and there's going to be a section of time round about, or time and space round about here, where this left wheel is going to be travelling more slowly than this real wheel over here. And so because this wheel travels more slowly, this wheel travels more quickly, it causes this turning motion in the truck. And so what we end up is, if we imagine, I'm going to draw some lines here coming in, this is a little bit like the same direction that my truck's taking. As it comes in, this one here, so this one carries on moving at the same speed, but this one here slows down. It's not moving as quickly. Same speed, slows down, not moving as quickly. And so we end up, then on this side, carries on, smaller wavelength now, but we've got a change in direction. So it's important to note now that this truck's changed direction, and it's got a decrease in the wavelength. It's moving more slowly in the mud, and because it's moving more slowly, in the same amount of time it covers less distance, so its wavelength is decreased. That's a similar effect as to what happens in the light. It's changed direction and it's reduced its wavelength. So the wavelength decreases, but the frequency remains the same. It's still the same number of waves being produced per second, but the wavelength is decreased and the speed decreases. This is it's fairly easy to see why this happens if we think about the wave equation. The wave equation is given like this, so that the speed of a wave is equal to the product of the frequency and the wavelength. And if the wavelength has decreased, well, the frequency remains the same, the speed is obviously going to decrease. Or it could be the other way, that the speed has decreased and that causes the wavelength to decrease. So we've got our change in direction, we've got a change in frequency, and we've got a change in speed. One little side point here that I really should make clear as well is that here at this instance we're looking for a decrease. The speed's decreased and the wavelength's decreased, but this is from when we're going from air to glass. So we get a decrease if we're going from something which is less dense to more dense. If we were doing it the other way, if we were going from glass to air, we would actually find that the speed increases and lambda increases. So it's the opposite effect. If you're going from something less dense to more dense, then the speed and the wavelength decrease. And if you're going from something more dense to something less dense, then the speed increases and the wavelength increases. And actually we get a change in direction to the other direction. So it's the reverse effect. So if this one, air to glass, caused a change in direction to the left, from glass to air would cause a change in direction to the right. And what type of lens is it? A convex lens. Absolutely, well done. So here we're going to show some light travelling towards our lens, and what I've shown here, these lines, these are the wave fronts of light, and we're imagining light acting very much like the water waves with the crests as they approach. And what's going to happen when this light approaches and hits this glass is it's going to cause a change in direction, like so. And this change in direction results in our wave being focused to a point here. So as the light comes through, as the wavefront hits here, it starts to change direction, and because we've got a curved surface, the amount that it changes by results in this sort of pattern. So light in the middle here, which is hitting it straight on, you notice there it travels straight through. It only, or the amount that it changes by, the amount that it changes direction depends on the angle at which it hits the surface. So if it hits the surface like this, we get a large change in angle. But if it hits the surface straight on, we get no change of angle. So we get a more extreme change at the edges, and we get a less extreme change in the middle, and that results in this curved focusing pattern. Now, we don't have to go into the geometry, we don't have to really go into a lot of detail here, but what we do need to know is that refraction takes place. Refraction, that's the effect causing this change in direction, and it's a result of the geometry of the lens. It's a result of the fact that it's got this very smooth curved surface, and the amount of curvature on this surface determines how exactly it goes through. But a shape like this, one of our convex lenses is always going to focus it like that, and one of our divergent lenses, or a concave lens, which we saw earlier, would actually have the opposite effect, and and the waves near the outside get refracted, and the ones at the middle go straight through. Something like this. So this is why a lens has this effect. Okay, so that was refraction. A couple of questions for you. Focal length. I mentioned this right at the beginning of this lesson, and I sort of breezed over it a little bit. What is the significance of focal length? Do you remember what it means? And do all lenses have the same focal length? So have a go at answering that for me, please.
Stop the tape.
Okay, so we'll now have a look at this, alright? So the focal length of a lens, and we'll come back to my convex lens here. The focal length is the distance between the lens and the focal point. And the focal point is the point at which all these sets of parallel rays come to be focused at. So if we've got an object over here that's shining light out in parallel directions, it will be focused to a point, and this point is the focal point, and this distance here is the focal length. And this is a characteristic length that depends on the geometry of the lens, or depends on its shape. So the focal length of a lens depends on the shape of the lens. Alright? And this is how it will vary. So I've got two situations here, both of which we've got sets of parallel rays coming in. So this is situation 1, this is situation 2. Parallel rays coming in at both cases, and in this first instance my focal point is here, and so my focal length is that. And in this second situation, this is my focal point. So my focal length is that. Actually, I'm going to call this one F1 and this one's F2. So you can see here that F1 is shorter than F2. So if you have more curved, that was a bad sentence, if you have a more curved lens, then you get shorter focal length. So that the larger the curvature, the shorter the focal length. If it has a short focal length, it is a high power lens. So a short focal length is a high power lens. This situation on the bottom, this is less curved. So we get longer focal length. It's low power. And in fact, there is a system that is used for rating the powers of different lenses, and the power of a lens and its units are dioptres, and has the symbol D. So it's dioptres or diopters. I'm not 100% sure on the pronunciation. Dioptres. It is given by 1 divided by the focal length, which is in meters. So this is a rating system used to say which is the most powerful lens. So you'll notice this is power is inversely proportional to focal length. So if it's got a very high focal length, so let's say we had something with, let's look at 2 examples, all right? So 1, what is the power when focal length equals 4 meters? 2, what is the power when the focal length equals 0.5 meters? Okay, do you want to have a go at those quickly?
Stop the tape.
And I will now also have a go. Okay, so the power is equal to 1 over 4 meters. So the power is 0.25 dioptres. And question 2, the power is equal to 1 over 0.5 meters. And then that is the same as 2 dioptres. Alright, so fairly straightforward, but we do need to make sure that we're doing it in meters and dioptres. A question might tell you, so question 3 might have been, find power when the focal length equals 20 centimeters. Have a go.
Stop the tape.
Alright, so if you're going to try and answer this question, same again. Power is equal to 1 over focal length, but the focal length has got to be in meters. So first I need to convert 20 centimeters into meters. So that's 0.2 meters. So that's 1 divided by 0.2, which is equal to 5.
Now it's time for our wrap-up. Let's give it everything we've got. Ready? Begin.
Alright, so it's time to wrap up, and we've been through quite a bit of information on lenses. I'm going to try and summarize it for you nice and quickly. Lenses are used to manipulate light. Two types that we need to know about: convex and concave. It's got a curving out shape, it's got a curvy in shape like a cave. So this is convergent, and this is divergent. So this one spreads it out. Okay, why the lenses work? Why does this happen at all? What causes this effect? It's a physical phenomenon called refraction. Refraction, it's a phenomenon that affects waves as waves move from one medium to another. So when I say medium, that's a substance through which a wave travels. So when a light wave travels from glass to air, or air to water, or air to syrup, or air to oil, or water to, whatever, when it moves from one substance to another, we get this effect, refraction. Well, what actually does that mean? What do we see happening then? We get a change in speed, we get a change in wavelength, and we get a change in direction. So if we get a change in speed, a change in wavelength, and a change in direction, this is the one that we're worrying about here at the moment with these lenses. That means that this means that we can focus the light. So we get a nice clear image formed at a particular point. And if we're forming a nice clear image that's coming in from light from a distant object, then we can look at it and we can study it. Now, we haven't made a telescope yet because we've only looked at one lens. In order to make a telescope, we're going to need to use two lenses for a telescope. I'm just going to put scope because I can't bother to write out the whole word. We need to use two lenses for a telescope in combination. We're going to have a look at that later, but our next video is going to focus on ray diagrams and drawing the path of light as it moves through lenses, because there's quite often questions about this on the P7 topic, and we need to be comfortable and familiar with how to draw and do and use these.